Have you ever wondered what's actually happening when the ground beneath your feet suddenly starts to violently shake? Well, according to ancient Japanese mythology, the culprit is Namazu. He's a giant, earth-shaking catfish with the islands of Japan resting squarely on his back. The myth goes that a demigod pins him down with a heavy stone. But, whenever that demigod gets a little distracted, Namazu thrashes and the earth just absolutely trembles. It's a beautifully vivid story, right? But as fascinating as that is, the real science behind what triggers these massive tremors is, honestly, even more mind-blowing. Welcome to The Explainer.
Today, we're putting the myths aside and going deep underground. We're going to track the true monster beneath, tracing the awe-inspiring and, frankly, sometimes terrifying science of how earthquakes are born, how they race to the surface, and how modern technology is quite literally trying to outrun them. Let's get into it.
Okay, to understand this true monster, we actually have to look back to the great 1906 San Francisco earthquake. After that completely devastating event, a scientist named Harry Fielding Reid carefully examined the shifting ground, and he developed what we now call the elastic rebound theory. This was the very first framework to actually explain how seismic energy spreads. You see, before Reid, people kind of thought the surface ruptures were just the result of ground shaking, but he realized the exact opposite was true. Rocks under immense pressure accumulate energy, they deform, and then, violently, they snap back into place.
Picture an animation in your head of the Earth's massive tectonic plates as these colossal puzzle pieces trying to slide past one another. But at the boundaries, intense friction locks them right in place. As the rest of the plate keeps pushing, strain builds up at that locked edge, slowly stretching like a massive geological rubber band. Finally, the rock's internal strength just gives way. Step 3. The snap. In a fraction of a second, all that pent-up energy violently releases. And that sudden release of elastic energy, that is your earthquake.
Section 1. Deep dives and megathrusts. So where on our planet are these geological rubber bands being stretched the absolute tightest? Well, the ultimate danger zones are subduction zones. This is where two tectonic plates converge and a dense oceanic plate is forced to literally dive deep into the Earth's mantle right beneath a lighter plate. These specific zones are absolute geological powerhouses. They're completely responsible for generating giant megathrust earthquakes, pushing up volcanic arcs, creating the deepest ocean trenches, and, tragically, triggering devastating tsunamis.
Zooming in on that boundary, we find the geological fault, the true nucleating surface for all this seismic activity. Immense pressure and friction lock these colossal slabs together. As they try to move, unimaginable stress builds right along this plane, sometimes for decades or centuries, until it finally ruptures, and that resulting slip is exactly what generates those massive megathrust quakes.
But here is where it gets really wild. Earthquakes don't just happen right near the surface. Way down in these subduction zones, we get what are called deep focus earthquakes. At depths of 300 to 700 kilometers, it's not just about friction anymore. The descending plate faces such crushing pressure and intense heat that the minerals within the rocks actually undergo a metamorphic phase transition. Their crystal structures rearrange and shrink in volume. It's like squeezing a rigid sponge until it just collapses. This sudden shrinkage causes the rock to brittly crack, unleashing a deep focus earthquake. Our planet is actively changing its own chemistry under pressure, and the result shakes the world.
Section 2. The shake race seismic waves.
Once that snap happens, whether it's shallow or super deep, the energy has to go somewhere, right? It shifts from a buildup of pressure to a high-speed underground race. The energy travels in different waves at vastly different speeds. First out of the gate are the P waves, screaming fast at 8 to 13 kilometers per second. Chugging along behind them are the S waves, clocking in at roughly 60 to 70% of that speed.
Now, these waves pack very different types of punches. Imagine an animation of P waves acting like sound waves. They're longitudinal, aggressively pushing and pulling the ground back and forth in the exact direction they're traveling, usually arriving as a quick, sharp jolt. But those slower S waves, they are shear waves. They violently thrash the ground perpendicularly, moving up and down or side to side. Because of this transverse motion, they cause significantly more damage to our buildings.
Because of their push and pull nature, P waves are basically the ultimate VIPs. They can blast through anything, solids, liquids, and even gases. But those destructive, shearing S waves, they can only travel through solids. If they hit a liquid layer deep underground, they are stopped completely dead in their tracks.
And if the P and S waves weren't enough to worry about, we have the late arrivals, the surface waves.
These waves, specifically known as Rayleigh and Love waves, don't plunge through the Earth's interior at all. Their journey is completely confined to the surface layers of the crust. They're the slowest of the bunch, moving at about 4 to 5 kilometers per second, meaning they're the absolute last to arrive at a seismic station. But do not let their speed fool you. Their complex, elliptical, rolling motions, honestly much like ocean waves, make them incredibly destructive to our surface infrastructure.
Section 3. Measuring the monster. Magnitude versus intensity.
So whenever an earthquake hits the news, you hear a lot of numbers thrown around, leading to the two most misunderstood terms in seismology. Let's clear this up right now. Magnitude and intensity are absolutely not the same thing. Magnitude measures the actual size of the earthquake right at its source, the total amount of energy released when the fault snapped. Every earthquake has exactly one magnitude, no matter where you are standing. Intensity, however, is a measure of the severity of the ground shaking at your specific location. Intensity changes depending on how far you are from the epicenter, the type of soil under your feet, and the depth of the quake. So remember, one magnitude, many intensities.
And the magnitude scale is not a simple 1, 2, 3 progression. An incredibly massive magnitude 8 earthquake does not release just 4 times more energy than a magnitude 2 earthquake. No way! It releases 792 million times more energy. It is an exponential explosion of power that is honestly almost hard for the human mind to grasp.
And that magnitude is directly tied to the physical size of the rupture area, the actual surface of the fault that violently tears open. A minor magnitude 3 quake, which you definitely feel by the way, has a rupture area of about 15 football fields. But an M8 megathrust quake? The fault snaps open over an area of 5,000 to 10,000 square kilometers. That is a tear in the Earth's crust roughly the size of the entire state of Delaware.
On the flip side, we measure intensity using the Modified Mercalli Intensity Scale, or MMI. Unlike magnitude, which is strictly calculated using seismic instruments, the MMI is entirely observational. It ranges from Roman numeral 1, which is imperceptible to humans, all the way up to X, which indicates catastrophic total destruction. It's a scale built entirely around what people actually feel and the physical damage done to our chimneys, our walls, and our cities. Section 4. The final race. Beating the quake.
With all this terrifying raw power, it sounds like we're just completely at the mercy of the Earth, but science is fighting back. We cannot predict earthquakes. No one can tell you a quake will happen next Tuesday. But seismologist Tom Heaton realized we don't actually need to predict them if we can just outrun them. Seismic waves travel at a few miles per second, but electronic alerts travel at the speed of light.
Let's trace this high-speed timeline, because it literally happens in the blink of an eye. The quake starts. Instantly, the fast P waves hit a network of sensors. Boom, data shoots to processing centers. Algorithms furiously calculate the threat, and a warning is blasted right to your phone. All of this happens before the highly destructive S waves even reach you, giving trains time to brake and giving you time to drop, cover, and hold on.
But sometimes you feel a quake and your phone just stays completely silent. Why? Well, there are a few reasons. First, the blind zone. If you are less than 10 miles from the epicenter, the P waves and S waves arrive almost at the exact same time. The computers just don't have those 5 to 8 seconds needed to process and warn you before the heavy shaking starts. Second, the shaking might simply be too weak to trigger a mass alarm. Or third, and check this later, your phone's Do Not Disturb or location settings might actually be blocking the lifesaver.
We've moved from the myth of a giant catfish to the incredible reality of elastic rebound, crushing deep focus phase transformations, and a high-stakes, real-time technological race against the rawest power on the planet. Our early warning systems are amazing, but they're a constant tightrope walk of physics and time. So I want to leave you with this. As our algorithms continue to race against the sheer speed of seismic waves, when the locked plates finally snap, how many critical seconds will you have to brace for the monster beneath? Thank you for checking out this explainer. Stay safe out there and keep exploring the incredible science of our dynamic Earth.